Chapter 2.4, Complex Numbers. Our goals are to use the imaginary unit I to write complex numbers, add, subtract, and multiply complex numbers, use complex conjugates to write the quotient of two complex numbers in standard form, and find complex solutions of quadratic equations. So the imaginary unit I. Some quadratics have no real solutions. One example of this is like x squared plus 1 equals 0. So we know when we solve that, we get x squared equals -1, and then we square root. And so we're not allowed to have a negative inside. So what they created was the imaginary unit I. And so what that is I equals the square root of -1, or I squared can just equal -1. So for example, if you have -5 plus square root of -9, that changes to -5 plus 3i. Definition of a complex number is that a and b be real numbers. The number a plus bi is a complex number written in standard form. The number a is a real part, and the number bi, where b is a real number, is the imaginary part of the complex number. So a plus bi is a real number. A plus bi, when b is not 0, is an imaginary number, right? When b is 0, it's just a. And then when a is 0, it's a pure imaginary number. Every real number a can be written as a complex number using b equals 0. So for every real number a equals a plus 0i. So the set of real numbers is a subset of the set of complex numbers as shown in the figure below. So you have real numbers, imaginary numbers, and then our complex numbers. So quality of complex numbers, two complex numbers, a plus bi and c plus di, written in standard form, are equal to each other, if and only if a equals c and b equals d. So operations with complex numbers. To add or subtract two complex numbers, we're going to add or subtract the real parts and then the imaginary parts of the numbers separately. So let's just try this out. We have 4 plus 7i and plus 1 minus 6i. And so we're going to add the imaginary part, or the real parts, together. So we're going to add 4 and 1, and then we'll add the 7i and the -6i. So what we're going to get is 4 plus 1 is 5, and 7 minus 6i is, let's see, 5, and that is just an I. Then we'll do the next one. 1 plus 3 is 4, plus 2i minus 2i is 0. So just 4. So here we need to make sure and distribute the negative. So this is 3i plus 2 minus 3i, then minus 2 minus 5i. So 3i, that cancels out. 2 minus 2. So this answer is -5i. For the last example, we have 3 plus 2i plus 4 minus I minus 7 minus I. So let's add. So 3 plus 4 is 7. 7 minus 7 is 0. Then 2i minus I, that is going to be 2i minus 2i, or 0. So go ahead and try these examples down here. Pause the video, and when you come back, I will have the answers for you. So if you tried this out, you'd have gotten 12 minus I, -2 plus 7i, -6 plus I, and 0. So just as a reminder, you have to write it in standard forms. That means that the real parts go first, a, and then the bi goes second. So let's do multiplying complex numbers. It's very similar. And so we'll multiply. We get 4 times -2 is -8, and then 4 times 3 is a positive 12i. Then the next thing we could do FOIL. 4 times 2 is 8, plus 6i minus 4i minus 3i squared. So we need to simplify. We have 3i squared. And remember that I squared equals -1. So we have 8, and then plus 6i minus 4i is a positive 2i, minus 3 times a -1. So that's going to end up being a positive 3. So 8 plus 3 plus 2i equals 11 plus 2i. The next one, we know this is the a plus b, a minus b pattern. So this is 9 minus 4i squared. So this is 9 minus 4 times a negative 1, or 9 plus 4. So this answer is 13. The last one, this is 9 plus 3 times 2 is 6, so that's 12i plus 4i squared. So this is 9 plus 12i plus 4 times negative 1, or 9 minus 4 plus 12i. So this is 5 plus 12i. So go and try these next examples down here, and pause the video. When you return, I'll have the answers for you. So if you tried these examples, you would have gotten negative 15 plus 10i, 18 minus 6i, 41, and 12 plus 6i. Hope this helps. Thanks for watching.